Hello 8th graders, this is Mr. Humphreys, and we're going to take a break in Chapter 2, and we're going to skip ahead to Chapter 12 to extend what we already know about transformations. Chapter 12 covers transformational geometry, so we're going to extend what we already know. In this video, we're going to actually go over a few sections all at once, since you've already had a lot of this information. But we're going to take it one step further. So we're going to start with 12.1, reflections. Our first vocab word is isometry. An isometry is a transformation that does not change the shape or size of a figure. There are three transformations that do this. They are reflections, translations, and rotations. They are all isometries. Isometries are also called two words here: congruence transformations or rigid motions. Now this is just review, so you do not need to write this down, but we're going to review that if you remember that in a reflection is a transformation across a line called the line of reflection. So this white line right here is called the line of reflection. The line of reflection is the perpendicular bisector of each segment joining each point in its image. So A to A prime, if we connect A to A prime, we know that the line of reflection is a perpendicular bisector, which means they're perpendicular, form 90-degree angles, and the distance from A to A prime is bisected. Therefore, from the line of reflection to A prime and the line of reflection to A, each of those segments would be congruent. So we're going to start with our first example, which is a problem-solving application. This is found on page 825 in your book. A trail designer is planning two trails that connect campsites A and B to a point on the river. He wants the total length of the trails to be as short as possible. Where should the trails meet? So when you're looking at this problem, let's understand what it's asking. The problem asks you to locate a point on the river. This point has to be somewhere in this river where the value, let's call it x, so that ax plus xb has the least possible value. So you don't know, is A to B here to here, here to here, here to here? The path could be any of those places. However, we need to make sure that it has the least value possible. This is where reflection comes in. We can actually reflect B or A, either one. We can reflect B across the river because the river becomes the line of reflection. So if we cross B, we can call it B prime, and then we can actually connect A to B, and right there, that shows us that where it crosses the river, we can call it point X. If we connect X to B, that becomes the shortest route from A to the river to B. We used reflection to show that. Now, if you wanted to verify your answer, you could actually measure the distance from A to X and X to B, and then pick X anywhere on this line, so you can put X here or here or here. You will find that the shortest distance, if you measure, would be X, located right here, where A to B prime, since B is reflection, where it intersects the line of reflection. On the top of page 826, you will see a Know It section. This is titled Reflections in the Coordinate Plane. Now, if you were reflecting across the x-axis or y-axis, or across the line y equals x, they give you a little bit of a cheat sheet on how to do that. So, for example, if we're just looking at this, if you're going to cross the x-axis and you have point P and it becomes P prime, the x value remains the same, but you take the opposite of the y value. If you're going to cross the y-axis, the y values stay the same, but the x value becomes the opposite. If you go across line y equals x, example here, p, which is xy, it's going to become yx, which means you just flip the x and y around. So let's look at example 2. Reflect the figure with the given vertices across the given line. Now these can be easily done by actually graphing, but we can actually use the chart we have up top, and we don't have to graph. So let's go to part A. We're going to reflect part A, which is triangle MNP, across the y-axis. So if we use the chart for across the y-axis, all it says to do is to take the opposite of the x value. That's it. So m prime, if we take the opposite of 1, would become -1, 2. N would become n prime, and the vertices, or the ordered pair there, would be -1, 4. And P becomes P prime, and that would become -3, 3. That's it. Part B, we're going to reflect the quadrilateral DEFG, which actually is a trapezoid. We're going to reflect it across y equals x. So according to the chart over here, I'm just going to reverse them. So D prime becomes 0, 2. E prime would remain the same as 2, 2. F becomes F prime, which is 2, 5. And G becomes G prime, which is 1, 5. All I did was reverse the order of the x and y. In section 12.2, we're going to talk about translations. Now, once again, as you know, a translation is a transformation where all of the points of a figure are moved in the same direction, the same distance. A translation is an isometry, so the image of a translated figure is congruent to its preimage. Translations are what you've used to describe right so many units and down so many units, or left and then up. A translation is when you slide something. So let's look at our first Know It section. A translation is a transformation along a vector, such that each segment joining a point and its image has the same length as the vector and is parallel to the vector. So here's the translation vector. Now, something you may not know, but I'm going to tell you right now that if you see these little arrows, these red arrows, that means they're parallel. So here's our translation vector. A to A prime is going to go in the same direction as the translation vector. These two lines have to be parallel. So let's do an example. So if we just look at an example, and this is actually example 1, example 1 says, copy the triangle and the translation vector. Draw the translation of triangle along vector V. You'll notice that is the symbol for a vector. So here's our blue shape. This is the pre-image. Here's our vector. Each of our lines have to be parallel to our vector. So we're going to draw a line parallel to the vector through each vertex of the triangle. Notice that here's our vertex. We have 3 of them. We have to move all 3 points along that vector. Now, measure the length of the vector. Here's our vector. Then from each vertex, we're going to mark off the same distance as the vector. So the distance from this ray you see here, from here to here, we're going to move each point or each vertex on that triangle the same distance parallel to the vector. We then connect our triangle, all 3 points, and we have our new image that has been translated the same distance and direction as our pre-image. All right, so you may say to yourself, well, that's kind of weird. Why can't I just slide it right and slide it up, or slide it down and slide it left? You are going to do that. So we've made a little chart here. And there's something that you probably don't know, but it's right here at the top. And so if you don't know this, make note of this. Recall that a vector in a coordinate plane can be written such as this. It's not parentheses. This is how you write a vector. A represents the horizontal change. B is the vertical. Remember, the first number is x in an ordered pair. That's horizontal. The second number is vertical, which represents y. From the initial point to the terminal point. So, if we're looking at this, a horizontal translation, it's taking what you already know and putting it in correct geometric terms. So we want to make sure that the geometry terms are correct. So if you look here, xy is moved to the right. So if we go left or right, we are only going to be changing the x value. So your vector, A, is the change in x, and 0 means y doesn't change. So all you do is do the same thing on your x value. Vertical translation, B, goes up or down. That means the y value is going to change. So you're going to take your vector, your change in y, and you're going to actually do that to the y value. If you're moving both A and B, then whatever A and B are, you're going to make that change to the x and y coordinate. Looking at example 2. Translate the triangle with vertices A, B, and C, and you can see the ordered pairs, along the vector 2, 4. So as you remember, this represents, let me actually do it in red here. The first value of the vector represents your horizontal change. The second number in the vector represents the vertical change. So all this means is that you're going to take the image, and if you remember, we have xy, and that is going to be going to x plus 2, since we were going as a positive change of 2 in x, and a vertical change in y of plus 4. So we're going to take each of our ordered pairs, and we're going to add 2 to the x and 4 to the y. So A prime would become 0, 0. B prime would be 1, 2. And C prime would be -1, 4. Our last example is example 3, an application problem. In a marching drill, it takes 8 steps to march 5 yards. A drummer starts 8 steps to the left and 8 steps up from the center of the field. She marches 16 steps to the right to her second position. She then marches 24 steps down the field to her final position. What is the drummer's final position? What single translation vector moves her from the starting position to her final position? So since she starts 8 steps left and 8 steps up, her position would be the ordered pair -8, 8. She then has to move 16 steps to the right. Well, 16 steps to the right means that you're going to add 16 to the x value, since that's a horizontal change. So her new ordered pair would be 8, 8. She then moves down the field 24 steps. So that means that's a change in y, so we subtract 24 from the value of 8 in the y coordinate. That gives us her final position, which is 8, -16. The second step says to find the single translation vector that moves her from the starting point to the final position. Well, since she moved a horizontal change of 16 and a vertical change of -24, the vector would be 16, -24. Our vocabulary from these two sections is isometry.